Hi everyone, this is my new video on the topic of longitudinal by chronometer, or longitude by chronometer rather, long by chron as it is normally called. This question is from exercise 8, Captain Subramaniam's book on the practical navigation series. Deals with a question that involves sun as the celestial body. I have previously made videos on this topic, but I could see that a lot of the subscribers were not very clear on the concepts. Maybe I didn't do a good enough job and they were unhappy and they were posting questions and there were some genuine queries. So I thought I will take up a new question and discuss it, and hopefully it should clear your concepts further. This is based on the questions I have been getting on that topic, especially how to determine whether it is P or LHA towards the mid of the question. So let's get started without further ado. The question is on 31st of August 1992. It's PM at ship. That means it's evening at the ship. It's post 12 o'clock in the afternoon, and the dead reckoning position is 10 degrees 11 minutes south and 0 degrees longitude. The sextant altitude of the sun's lower limb was 39 degrees 15 minutes and the chronometer was running 1 minute 30 seconds fast. The time showed on the chronometer was 3 hours 11 minutes and 20 seconds. If index error was 2.5 minutes on the arc and height of eye was 17 meters, you have to find the direction of the position line and a position through which to draw it. Alright, so let's get started with the question. Of course, you need the 1992 Almanac for it. You can easily get it once. If you don't have it, just Google 1992 Almanac and you will get it. So don't worry about it here. You just see the process that I follow to solve this question, and the process remains the same. Doesn't matter which year it is. So no worries with that. Alright, so here I have started the question a little bit to get a head start. Otherwise the question becomes very long. So we've written the chronometer time which is given to us, which is 3 hours 11 minutes and 20 seconds. Now when the chronometer time is given to you as 3 hours 11 minutes and 20 seconds, it could mean 3 in the morning or 3 in the afternoon. We don't know. It's just like an analog watch. So if I have an analog watch with numbers written on it and it shows 3 here, this is how it looks like on the chronometer. So when you see 3, you don't know whether it's 3 in the morning or 3 at night, especially if you are away from the GMT. Now you might say that of course it's common sense, I know what time it is at GMT, but for academic purposes here, we don't know. We don't know the time at GMT. That is the time that the chronometer shows, time at GMT. So we don't know it's 3 in the morning or 3 at night. So what I do is I normally write the chronometer time as given to me, 3, 11 and 20. And then what I do is I add 12 hours to it, because it could be 3 in the afternoon as well. So I will determine whether it's 3 in the morning or 3 in the afternoon by adding 12 hours to the time given to me. Then the error given to me is 1 minute 30 second fast. If the error is fast, I will subtract it. If the error is slow, I will add it. Here the error is fast, so I subtract 1 minute. So this is hours, minutes and seconds. Make sure you write it under the minutes and seconds column. So the same thing that you do in the other column as well. So subtract the fast error from the time. So 3 hours 11 minutes 20 seconds minus 1 minute 30 seconds gives you 3 hours 9 minutes 50 seconds. Again, it's self-explanatory. So you can borrow 60 seconds from here, mix it 80 minus 30 is 50, and then this becomes 10 because you borrowed one whole minute to the second column. So then, or you can just put these values in the calculator and you will get the answer, whatever works for you. Then we have the zone. The zone depends on, of course, the longitude, and I round it off. So what you have to do is basically, to find the zone, you have to divide the longitude by 15. This zone tells me what time zone I am in, right? In this case, the longitude is 000 degrees 00 minutes. So if you divide it by 15, you still get 0. That means you are in zone 0. That means that you are in the time zone of the GMT. So if this is your GMT, this is the longitude of 000 degrees 000 minutes. So either side of GMT, 7.5 degrees east and 7.5 degrees west, is actually zone 0. So I didn't have to divide it, but I wanted to show you what zone is. So that means your ship is somewhere in this zone. Zone 0 means that all the countries in this zone, all the ships in this zone is keeping the same time as GMT. That is why no correction is required in the zone row. So here, even if it is plus or minus, so sorry, is this given to us? Whether, no, longitude is not given as west or east because it's 000. So how can 0 have any west or east? It's 000. It's a reference point. So it doesn't matter. So again, then it doesn't matter whether it's plus or minus, because you can't add or subtract because you don't know exactly what time zone you are in. I mean, whether you are in west or east. So because it's 0, it doesn't make a difference. So I will keep it at 0, plus minus doesn't make a difference. Whether it's plus or minus, it will not make a difference, right? Because it's 0. So the ship's time that you get is 3 hours 9 minutes 50 seconds, and in this case you get 15 hours 0950. Now the question tells you it's PM on the ship and it's 29th November. So out of the 2 times that is given to me for ship, what I see as PM means post 12 o'clock in the afternoon, is this time here. This is the ship's time. So it's 29th. Sorry, I don't have 29th November, it's 31st August. I'm mixing it up. So 31st August it is, not 29th November. So 31st August, right? 31st August, it's 15th. So 31st August PM is 15:09 and 50. So that is the PM time. That is the PM time. So if it is 31st 15:09:50 and you are in the same time zone, so time at the GMT is also 31st August 15:09:50. So automatically you know that the GMT time which you need to get into the nautical almanac will be 31st of August, and you better write it down separately so that you don't get confused like I was getting confused. I was looking at another question where the date was November, and that's why you see I was getting confused. So don't do that. Make sure you write it down separately. Is 15:09:50 is the GMT time, and this is the time and this is the date you will be using to get into the nautical almanac to get your other values. So what are your other values? You can start right with GHA sun. Alright, so I don't want to confuse you guys. If I draw my sun here, this is the way I work actually, but I don't want to confuse you. So GHA sun, I draw a sun here. Then you have increment, which you will always add. Increments are always added, and you will get GHA sun corrected, right? Then you can write down the declination, the D correction, and the declination corrected for the time. Then you can write down the latitude value. These are the things you will be needing. And on the other side, you can write down sextant altitude, index error, observed altitude, apparent dip or height of eye. I will explain how to get these values. And then you get apparent altitude, you get total correction. So the reason I didn't write these values beforehand is so that you know what these values stand for, because I'm writing an abbreviated form of it. True altitude, right? And then minus 90 degrees. And then you have true zenith distance. All right, which you get after you subtract the true altitude from 90 degrees. So these are the values you will be requiring to get into the almanac and finding the answers. All right, so what I will do is basically I will go into the almanac, and for the different values and for this date and time, I will find out all the different values at one time so that you don't have to go back and forth, and you can see how I find out all the values at one go. All right, so I will go into the nautical almanac now. This is my nautical almanac for 31st of August. You can see at the top there the date is written 31st August 1992. The first thing I will do is find out the GHA sun for 44 degrees 57.7, so which will be 44 degrees 57.7. So GHA sun for 31st August and 1500 hours. So you can see on the side here the time is written GMT time. This is 1500 hours. So if I go back, just let me switch on my pen here. So my pen is on now. So if you see on the side here, this is 1500 hours, right? And if you follow this row here all the way to sun, so this is star, so this is sun column. So this is where your GHA sun is for 1500 hours on 31st August, 44 degrees 57.7 minutes. Same time you can note down the declination, which is 8 degrees 24.2 minutes north. Now why I'm showing you all these values at one point of time, because I have made videos like this many times. I'm sure you guys are very familiar with how to find values from the nautical almanac. So let's not waste time going back and forth. I can show you all the values at the same time. So while you are noting down declination, you have to also note down whether the declination is increasing or decreasing to the next hour. You can see the declination as you go from 15 to 16, the declination is decreasing. So this is used to apply the D correction. Now what is D correction? We'll find out the D value from the bottom of the nautical almanac. Here D0.9 is the D correction value. Now we have found out what we need. Now we will go to the increments page for 9 minutes and 50 seconds. 9 minutes and 50 seconds, we'll go to the increments page, and which will be towards the end of your nautical almanac. So just go to 9 minutes and 50 seconds. There you go. You have 9 minutes and 50 seconds here. So you have 9 minutes here. So if you go to 9 minutes and you go to 50 seconds here, all right, so you can see here for 9 minutes and 50 seconds. Again, my pen is on. Yes, it is on. So this is the increment. This is the increment that you will add to the GHA of the sun that you have just found out. All right. And then you also found out that the D correction is 0.9, and the D correction and the declination value is decreasing as you go from 1500 hours to 1600 hours. So you come to this column here. You can see the column here, V or D correction. You go to this column here, then you find out for 0.9, it is 0.1 is the correction value. This is the correction value, 0.1. So you will take this and go back to the page from where we were writing the values. All right, so I will go back to where we were writing the values here. So you can see here, GHA I will write down as 44 degrees 57.7 minutes. Increment I will write down as 2 degrees and 27.5 minutes. And when I will add the two values, I will get 47 degrees 25.2 minutes. All right, declination also, you saw how I found that out, 8 degrees 24.2 minutes north. Then the D value was 0.9, and because the declination was decreasing to the next hour, I will put a negative sign here. The correction value was only 0.1 minute, and the declination corrected is 8 degrees 24.1 minute north. All right, write down the latitude given to you in the question is 10 degrees 11 minutes south. Now the sextant altitude again is given to you in the question. If you go up, you can see the sextant altitude is given to you as 39 degrees 15 minutes. Make a note of the lower limb. This is an important information. So when we apply total correction, so sextant altitude is 39 degrees and 15 minutes. Index error is on the arc given to you again. When it's on the arc, you will subtract it, minus 2.5 minutes. You subtract index error on the arc, you will get 39 degrees 12.5 minutes. Height of eye or dip is 17 meters. Height of eye is 17 meters. So you will have to go into the nautical almanac and find the correction for height of eye. So here I have to go a bit back and forth because I have to show you guys, otherwise you guys will get confused. So I will show you how I found out the height of eye correction for 17 meters. So in your nautical almanac, the very first page is this page here, which gives you the height of eye. So if you go zoom in here, this is the height of eye table. All right, it says dip here. This is the height of eye correction. So 17 meters will be lying somewhere between 16.9 and 17.4, and the correction is minus 7.3. All right, so here you will take this value. We'll have to come back to this page to apply the total correction as well. So let's do that soon. So you will apply negative 7.3. Remember, we are writing everything under the minutes column. So you will get 39 degrees 5.2 minutes. Now you take this 39 degrees 5.2 minutes, note down the lower limb information, note down the month of August, and now we go back to the nautical almanac again. So here we are going to apply the total correction for sun. So for sun, the total correction of August will be between April and September. All right. So the apparent altitude value is 39 degrees 5.2. You go down this column here, 39 degrees 5.2 will be somewhere here. Now because you are lower limb, you can see the lower limb values are given here. Now we are between August. So we are in August, which lies between April to September. That's why we are using this column. All right. So this column here, 39 degrees 5.2 is the apparent altitude value. For that you get a lower limb correction of plus 14.8. There is no interpolation involved in these kind of corrections. You just take the value and you apply it. So you apply plus 14.8. When you add the two, you get 39 degrees 20 minutes. Subtract it from 90, minus 90 degrees, and you will get a true zenith distance of 50 degrees and 40 minutes. All right, so half of your question is now done. So you've got your true altitude, you've got your true zenith distance as well. Now the important bit comes. This is where the students are getting confused, also abusing me online that I have not done a good job. So let's get started. So what the rule here is that, of course, you can use Haversine tables, but what I like to use is not Haversine. I used to use them when I was a cadet. Now, of course, scientific calculators are available. So we use scientific calculators, and we will use scientific calculators here as well. So we will use a formula that is supported by the scientific calculator, and we will use it to solve this question. All right, so let's get started. So we have a formula for this. We have a formula which says cos P. P stands for, let me explain it later. All right, so we are trying to find the LHA here. That is our objective. Let's make it simple. And the formula is sine of true altitude plus or minus. I will explain why this is plus or minus, depends on a certain criteria. Sine of latitude multiplied by sine of declination divided by cos of latitude and cos of declination. All right. Now, what is this plus or minus? Now, if the latitude and declination, if they are the same names, it will be minus. If they are opposite names, it will be plus. So, latitude and declination, look at latitude and declination here, they are the opposite names. They are not the same. They are both are north and they are both are not south. So, it will be contrary names, it will be in addition. So, I will get rid of this subtraction sign. All right, so we will keep addition, and then it's simply a question of putting the values. So you put the value sign, and remember it's true altitude, not zenith distance. So sometimes you make a mistake and you put true altitude, you put zenith distance here, but put true altitude. All right, and you put sine of latitude, put sine of declination, put cos of latitude. Sorry, I should be putting the values. Cos of 10 degrees 11 minutes multiplied by cos of 8 degrees 24.1 minute. All right, so we get cos P equals, if I start solving this, what I will be getting is 0.63383 plus 0.02583 divided by 0.97368, and we can keep going. Make sure you get these values because this will get you the right answer. If you are not getting these values, please check your answer again before you start abusing me online. So 97368 and cos of P, which will get you 0.67749. All right, and then you have P is equal to cos inverse of this value 0.67749, and you will get P as 47 degrees 21.1 minute. Now, is this P or is this LHA? Now, this is the main question that all the students ask me, and they are confused, and maybe I didn't do a good enough job. Let's accept it in my last videos and on long by Chron. So let me explain to you a couple of different ways that you can find out whether this is P or LHA, how to use this value. Now, let me explain what is given in the books. Now in the books, what is given is that if it is before meridian passage, then LHA equals 360 minus P. If it is before meridian passage, so if it is before meridian passage, LHA will be equal to 360 degrees minus P. All right, so in this case, of course, we have to first find out whether it is before meridian passage or not. If it is after meridian passage, then it says LHA equals P, means you take the same value and use it. So this is one of the ways. Let me explain how to use this way. Now what do you do? How do you know whether it's before meridian passage or after? Now this rule applies to sun only. I will explain what happens with star in the next video that I make on star. Now you can see the local time here. The local time is 15:09:50. That means it's already past 12 o'clock. Normally when the meridian passage occurs, it occurs in the noon time. It occurs at 12, somewhere close to 12 in the afternoon. It's already past meridian passage. It is 3 in the afternoon, 15:09:50 p.m. So it is 3 in the afternoon. So it is after meridian passage. That means you will use LHA equals P. Now you may ask me that, okay Sam, this works in this case, what about star? You know, in star it's hard to determine meridian passage, and you are right, it's hard to determine meridian passage because we don't know at what time meridian passage is occurring with stars or moon or planets. So what do you do in that case? So in that case, what is recommended in the book, maybe you don't understand, or what is recommended by me as well, I always like diagrams, you know that, right? So this is what I do. So this is rule 1. This is one way of doing it. I will put not rule 1 but way 1. And what is way 2? Way 2 is for me drawing diagram. It's very simple. It makes your life easier. Alright, so what you do is that draw a circle. Alright, put here right Greenwich meridian. Now this is celestial Greenwich meridian. Alright, now what do you know about the GHA of the sun? GHA of the sun is 47 degrees 25.2 minutes. What is GHA? GHA is measured westward from Greenwich meridian towards the body. So if I go westward, I have to go to my left. I have to go this way. This is westward. Alright, so this is westward and this is eastward. So GHA is measured westward from Greenwich meridian, celestial Greenwich meridian, to the body. So approximately this is where the sun is. This is the GHA of the sun. This is the GHA of the sun, 47 degrees 25.2 minutes. What else do you know? So what else? We don't know LHA. Here we are just found out P. The confusion is whether P should be used as P or whether it should be used as LHA. So don't count LHA so far. Then we know is our approximately DR longitude. Now DR longitude gives us an idea of our longitude. It's not too far from where we are, but it is not very accurate either. But it still tells us an idea where we are. So our DR longitude given to us in this case is 000 degrees. Alright. So 000 degrees means we don't go west or east. We are at the Greenwich meridian. We are also here. Alright, we are also here. This is us, observer. Now the question is, what is LHA? LHA is nothing. I'll change the color of the pen. LHA is nothing but again the angle measured from the observer's meridian to the celestial body measured westward from the observer. So if I go westward from you as the observer, where do I reach? I reach here. That means that in this case, LHA is almost 47 degrees something, right? So of course you will say it is you cannot say that LHA equals exactly GHA, but here the angle you get, this is LHA. That means the angle is not more than 47 degrees, somewhere very close to 47 degrees. Alright, here we can't say LHA equals GHA exactly because that's not how it works, but you get an idea here. The LHA is close to a value of 47 degrees, right? It cannot be 360 minus 47, which will be close to 313 degrees. This angle is not 313. It is close to 47 degrees. It is almost equal to GHA. Therefore, you know that in both the methods, whether we say LHA equals P or whether we use this method, we know that LHA will be close to the value we have found out, which is P, which is 47 degrees 21.1 minute. This is the second method of finding out what is LHA. LHA you will use as 47 degrees 21.1 minute. And once you have confirmed this with the diagram and also the rule of meridian passage in case of sun, in case of star, moon, planet, we will only use way 2. We cannot use way 1 because we don't have an idea of when the meridian passage occurs unless you are experts in celestial navigation, which I am not, unfortunately. Alright, so we get a brief idea of our LHA here. Now once you have determined what is LHA, forget about P. You only call this LHA. Don't call it P and start getting confused. Don't call it. Alright, you use this as the LHA value. LHA value is 47 degrees 21.1 minutes. So we will say LHA is equal to 47 degrees 21.1 minute. Alright, GHA you have already found out of the sun is 47 degrees 25.2 minutes. Alright, now once you subtract one from the other, always subtract the bigger number, always subtract the smaller number from the bigger number. So GHA minus LHA will give you longitude in this case. Here the longitude is 000 degrees 04.1 minute. Now you have to determine whether it's east or west. You can already see that the GHA is more than LHA. Alright, so when GHA is more than LHA, GHA best, longitude is west. GHA is more, longitude will be west. So here we have west. GHA least, longitude east. If GHA was less than LHA, longitude would be east. That is how you determine longitude. So you have determined longitude now, your job is done. However, that is not what the question wants. The question wants you to also find out what is the direction of the position line and a position through which to draw it. Alright, so you have found the position, you have found out the long already. So now you have to find out the position line. So from here onwards, forget about P and all that. Use LHA. Otherwise, you will get confused. Alright, so what we say is that, let me change the color of the pen again. We find out A, which is tan lat by tan LHA. I am not using P anymore. But the funny thing is, even if you use P or whether you use LHA and the values are differing. So in this case, if you were using 47 degrees, 21.1 minute, or if you subtract it from 360 and use that 313, you will still get the same answer. But don't confuse yourself. Once you have determined P equals LHA, use LHA. Once you determine what is LHA, use LHA. Forget about the word, the letter P. Alright, so here tan lat by tan LHA, just use what you know. So tan 10 degrees 11 minutes divided by tan of what you know, 47 degrees 21.1 minute. What you will get is 0.17. Now here, whether you get negative or positive answer, you will ignore the negative sign. You will always write a positive number here. So the rule of LHA, or rather, sorry, rule of A or naming A is that A is named opposite to latitude, unless LHA is between 90 and 270. Here LHA is 47 degrees. It is not between 90 and 270. So I will name it opposite to latitude. So my latitude is south. It's 10 degrees 11 minutes south. I will name this north. B is tan of declination divided by sine of LHA. So tan of 8 degrees, what is the declination? I have to keep going back. 8 degrees 24.1 minutes. And sine LHA is 47 degrees 21.1 minute. I will get 0.20. Now declination named same as, sorry, B named same as declination. So my declination was north. I will name it north. Now what is C? C is A plus B if both are same names. If they are different names, it will be A minus B. Alright, so A plus B, because A and B are both north, in this case I will add the two, 0.17 plus 0.20, I will get 0.37, and because both are north, I will name it north. And then we have tan azimuth equals 1 divided by C times cos of latitude, which is equal to 1 divided by 0.37 multiplied by cos of latitude is 10 degrees 11 minutes. So here often in the calculator what students do, they just put 1 divided by 0.37 multiplied by cos of 10 degrees 11 minutes without using bracket. Don't do that. Calculator will get confused, you will get the wrong answer. So either you solve the denominator first or you put the denominator in brackets when you put these values in the calculator. Otherwise you will get the wrong answer. Alright, so here azimuth equals, this is tan azimuth. So azimuth will be equal to tan inverse of 1 divided by 0.36417, which is 2.74597. What you will get is close to 70 degrees. We get 69.98 degrees. Now in the book, of course, the answer is 69.98 degrees. You can work with this, or I like to round it off. And this is what I tell my students, because azimuth is a bearing. Remember that. Bearing cannot be 69.98. So you can round it off to 70 degrees. Both the cases, you should get the right answer. You will get the marks, because in the book it is 69.98. I like to round it off to 70 degrees. Now you have to name it. How do you name it? What is name of C? So name of C is north. And what is LHA? LHA is 47 degrees 21.1 minutes. So if LHA is between 0 to 180, you will name it west. If it is greater than 180 to 360, you will name it east. So in this case, LHA is what? LHA is west. Okay. And name of C. This is name of C. C was what? C you could see is north. So I have named it north here. And this is west here. So whether you want to continue with 69.98 or whether you want to continue with 70, it's your choice. I will explain one of them. All right, so what is north 70 degrees west? North 70 degrees west, this is north, this is west. North 70 degrees west means you are going from north 70 degrees here, right? So if this is 360, going north 70 degrees there, so 360 minus 70, which will be equal to 290 degrees true. All right, north 70 degrees west, so going from north towards west by 70 degrees is 360 minus 70 is 290 degrees true. Now how to find the position line? Just go plus 90 minus 90. So if you do plus 90, what you get? 380. There cannot be a 380. So 380 minus 360 is 020. And minus 90, you get 200. So this is the direction of position line. So the bearing is 290 and the direction of position line is 020 to 200 degrees. And what is the position through which it will go? Longitude you have calculated already as 000 degrees, 4.1 minutes west, and you use the DR latitude, of course, in this case. Right? So I hope guys I answered your queries. I have been getting lot of complaints, lot of abuses online, and I thought of making this video, but I wasn't getting time. So please let me know if this helps or not. I will be making videos on all the questions, all the unsolved questions in long by Chron, whether it's star, sun, moon, planet. You will get answers to all. I will explain all of them. I will keep repeating my explanation till you understand it. Thank you for watching today's videos, guys.